Is it? Okay. Okay, for those who have already logged in, take your attendance. Later on at about 4 o'clock, when we take a break, I'll continue to give you a chance to take the attendance as well. Right? People keep coming in. Okay. Now I hope that everyone see me and can listen to me. The sounds looks good. How are you? It's a new week again. I think we are nearing the end of the course, but I think this semester it's kind of lengthy, so I do not actually check when we should stop our teaching. But I am planning to finish up our course within these few weeks. So there's one more test we have to conduct. So probably we'll have to conduct the test sometime next week. And at the moment, we also have a project to do. So you have to carry out a project. Now, the time length for the project is, get the people to come in first. Okay, so this is time we have to talk about our projects. Now, you have a lot of time for your projects because I think this semester, because of this COVID-19 thing, the grading marks has to be extended to a very late moment later. So you have about, my plan is to give you at least 4 weeks to finish your project. But in order to do the projects, I have to start choosing different types of project that you can do. So there's about 30 students in the class, so I have to prepare at least 15 projects. So the idea is that every one of you would pair up with your friends, right? So you should find a pair of your friends, and both of you will join together to do a project. So I have to prepare at least 15 projects, I think. So you click on the thing that I just uploaded in the e-learning. So this is the tentative link. So I'm going to find out a few more of these projects, but these are only tentative, okay? So for example, most of these projects are in the form of a simulation. So for example, if you click on this one, then you'll be linked to a file. You're supposed to download this file and see the simulations. So you can't see it here, I think. Maybe you can. Yeah, I can see the simulations. So your project is to simulate this kind of file. So I'm going to find out a few more such kind of simulations so that you can click on. I have not opened the choices. So the idea is that I'll give you about maybe like 15 or 20 different topics. Some of the topics are on simulation. Some of the topics are on calculations. Some are difficult, some are not so difficult. But you have to choose your project, and then I'm going to give you a Google form. So you choose your project and then you fill up the forms. Then you book the program. Now, once the project is booked by one group, then the other cannot book anymore. So one project for one group. So every groups of 2 persons would have 2 members, right? So you have about as many weeks as possible to finish the project. Then you have to submit the project, and you also have to write a report, not only to submit the project in the forms of the programming, but also a sort of a report that explains how you do the projects, and then what are the consequence, or what are the things that you learn from the project. So I'm going to tell you in more detail in a complete descriptions of how to carry out the project. So how long the project is tentatively 4 weeks, but I actually do not check in detail what is the deadline. I think the deadline would be set before the examination board meeting. The examination board meeting is a meeting where the school have to discuss on the grading. Right? Last time you have a final examination. Now you don't have final examination. So the the exam board will be held somewhere, maybe later on, a few months later, maybe 1 or 2 months later. So maybe 1 week before the exam board meeting, I have to collect all your grades, right? So that is the last day you are supposed to submit your assignment. So you're only going to choose the projects and then write a program, then write a project report on that, and then you submit. So last year, the seniors was also doing that. So you have to submit 2 documents, the program and also a project. So if you submit only the program without the project's report, then you get only half of the marks, okay? So, but this project is not meant to be comprehensive. At the moment, I'm still preparing more projects, so I have not done yet. Okay, so just to let you know about that. But in order to do some of the projects, most of these projects are simulation. For example, this one, the simulation projects can only be done if you know how to do simulation, right? So, so my target is to let you understand the simulations within, let's say, within this week. So this week we are going to do finish up the section part 9 and also part 10, which is on simulation. So you discover that in your ZCE 110, I think this one, you see that I have already uploaded the assignment on the chapter on assignment number 10. Okay, this is the one, this one. So I have not to decide whether I should add in another last topic, which is on Rayleigh algorithm. So if I have to check if we have enough time, then I'll add in one more simulations, which is on the Rayleigh algorithm. But if we do not have time, maybe we just stop at chapter part 10. Okay. So today we're going to finish up part 9, which is the second order differential equation. Last lecture also we have already finished with the section 9 on the second order differential equation. Okay, so let's look at the section 9, part 9. So I'm not going to edit this copy because this copy is the one that you see on your e-learning. So I'm going to edit work on this copy so that whatever I change will not be changed in your copy as well. Okay, so that the copy remains clean. Okay, so we are talking about second order differential equations. So this is an example that we have discussed, the second order differential equations for a simple harmonic motions. Okay, so last lecture I gone through it a little bit fast, but I hope that you have already experienced how you do it. Now, last week also we also mentioned about the assignment, I think assignment 9.8.1. So assignment 8.1, wait, I'm supposed to open this assignment 8.1, is containing 2 exercises. The first exercises is solving this first order differential equation simultaneously and then solve the second order differential equation. So if you have attempted these questions, then you should be able to finish up this assignment. So second order differential equation. So today we are going to look into more example of second order differential equations, which contain a little bit of physics of this damped pendulum. So solving a damped pendulum and the other second order differential equation are very similar. Okay, the formula for the differential equation may look different, but the idea is still the same. Okay, so what you need is to solve the second order differential equations by using the ODE solver, ODE INT. Okay, so let's begin our lecture on today, which is to solve the second order differential equations with these terms. And if you still remember what we have done last lecture, you have to break it down, right? So first order differential equation, you break it down into 2 equations. You have to define d dot, as a first order differential equation, then this second order differential equation have to be rewritten in terms of theta dot. Okay, so this is what we want to solve. So you introduce a new variable called theta dot, then you express the second order differential equation into the forms of d theta dot. So in terms of d theta dot, the original second order differential equation is then rewritten into this form. Okay, this form. Okay, so we are going to solve this. So in order to solve this, you have to define an differential equation. So basically, this is what we want to do. Since we have a little bit of time, now I would like to try this out. I'm going to try to cut and paste all this stuff. Not cut and paste. I'm going to reproduce the solution for this. Now, the solution is already been given to you, but allow me to go through this step by step so that you can follow me carefully better. Okay, so what we want is to solve this differential equation. I have to be smart because I tend to forget the syntax. But anyway, I'll try to go through this one by one again. So these are all the package you need. You need a size by integrate. Do you need this? No, maybe you don't need that. Size by integrate. Maybe you don't need that. Yes, no, yes, no. Maybe you don't need that. Size integrate is to integrate things. Okay, maybe you don't. Right. So what you need is an ODE INT. You need NumPy, and you need to plot the graph using matplotlib, pyplot. Okay. Then let us first define the constant. Now this is normally what we do, right? So when you write a program, you first have to perform what they call initialization. Initialization means you provide all the things that don't change in the beginning. For example, the constants that is involved in these equations and the numbers. So what are the numbers that's involved here? So these numbers called C, and then omega as well. So you have to provide what is a constant. So this is second order differential equation. Theta is the dependent variable. Independent variable is t. Right? I have said this many times, and I keep on repeating. I hope that you don't get bored with me, because I think some of you may not get it. When you have a differential equation, you have to be able to look at these equations and then tell yourself that yes, you understand that there are two kinds of variable: the dependent variable, which is a function you want to solve, and the independent variable, which is t. So this t will change, and this t is time. And what you want is to find out what is a theta as a function of t, and then plot it out. So this is our aim. Then the theta is a function of t. Here, c is a constant known as the c is the damping constant, and it ranges between 0 to infinity. And when c is equals to 1, then c is equals to 1, then is critical damp, right? So this c is a constant, and then this omega is the natural frequency of the pendulum. Okay, so if you have a pendulum, whether it is a spring or whether it is a hanging blob of ball with a length of L, then omega is a constant. Okay, so in this case, omega is set to be. So you have to provide what is omega and c before you can solve this equation. Okay, is there any other numbers you have left out? No, theta is what you want. C, theta, and t. So there's only c and omega. So you have to provide a number of c. So give number of c. So initially you make c as small as possible. Okay, maybe 0.1, and then so then you have to provide the omega. Okay, so omega is a number. You have to say what is your omega. So now omega in this case is related to the now maybe let's go back to this. This is the second order differentiation of a pendulum, and omega depends on the gravity constant and then length. So we have to express omega in terms of the constant g and L. So the frequency of a pendulum depends mostly on the length. So you have to set the length. The length is, say, 1 meter, and then G is 9.8. So G 1.8 is the constant, okay? So I have set up value of C, assign value of C, and then I'll assign G 9.81, and then omega. Omega is a constant, so when you change the length, then omega will become different, right? So if L, which length is shorter, then omega is larger. Now, then you have to decide how long you want to simulate the pendulum, right? The pendulum has a period. Period is related to the omega, 2 pi over omega. So this relationship between omega and T has to be well understood. You have learned this in form, form remove of form 1. Given the frequency, angular frequency, then the period is just 1 over T. So the period is just 1 over T. I think it's not stated here, but it should be understood, right? So the period is the time taken for the pendulum to complete one closed circle, okay? So then the time that you want to simulate for the whole pendulum in your simulations or in your calculations is then depend on how long you want to simulate, right? So simulate for 1 period, 2 period, 3 period. So we have to decide. So you have to express the length of simulation in terms of time in units of T, right? So we have said it many, many times. So the TRR should be NP dot lin space. So it's a number that starts from 0 second up to 1 T, and then say you have 100 points between them. But T is the last in the time variables. So that means if you do like that, that means your simulation only lasts for 1 period. So you want to see more oscillation, then you should assign, say, 5. Okay, just say 5. So if you want to make it 10, then you just change it to 10. So how many you want to change it? You just say NT lah. Okay, so I say NT equals to 5. So if you want a longer time, you just change the numbers of T period to be, say maybe NT, just to tell you that N is a integer, T refers to the period. So you want to have a simulation to be running for 5 period. So when you calculate, then when it oscillates, you see the solution should oscillate for at least for 5 periods, then you stop. So this is the initial length of time you want to do the simulation. So then let's proceed to the next bit. We have finished defining the constant. Then let us go to define the model. Okay, so the model again is a function. Define the model is a function that should return what? It should return 2 things. It should return the theta dot dt and also the theta square dt square. Okay, so when you finish this one, since we are going to solve a second order differentiation, the output from the model should be theta dot. Theta dot is just the first order differentiation of the function theta, and also theta dot. Right. So these are the 2 functions or value that should be returned by the definitions for the model. So within this model, we are going to define the problem. So we have to define what is theta dot and also theta dot dot. So theta dot. Now theta dot is what? Theta dot is the number that you should fit into the second order differential equation. While I construct the model, now let me say this is a solution we want to have. The solution is obtained by calling the ODE integrate. Then you provide the model. Then you are going to supply what? To supply the initial condition. Okay, the initial condition is supplied in the forms of an tuple. Okay, so what is this? There are two initial conditions to be supplied, the first one and the second one. Now, what is the first initial condition? As I mentioned again and again, for a second order differential equation, you have to supply the initial condition. You have to supply two initial conditions. That is the initial condition of theta at 0 and the initial condition of theta dot at 0. Like theta at time 0 refers to the initial displacement of the angle, and theta dot is the initial velocity of the angle in the beginning. So you have to decide, okay, let's just decide that initially the theta dot is, the theta at 0 is theta 0. Theta 0. This theta 0 refers to the angle when the pendulum is released. And let's just release it at 5 degrees. Right? So 5 degrees has to be expressed in terms of radian. So convert 5 degrees to radian means that you multiply by NP pi divided by 180. So this is a formula that would convert 5 degrees into radian. Okay, so we are going to release the theta from 5 degrees. So this is the initial condition for theta that would be supplied into the model when ODE INT is called. Then the second thing to be included into the initial condition is theta dot 0. Right? So initially it's released from rest. So theta dot is 0 now because we are released it from rest. Okay, so this is the initial condition that would be supplied to the theta dot. So this would be slot in. So once the ODE INT call the model, when the ODINT call the model, so it will first supply the initial conditions into the model, right? So the first number to be assigned to is the theta, and then the second number to be assigned to theta dot is the theta dot. Okay, so in your model, you have has a dependent variable. So this dependent variable has two components. The first component that would be supplied is the theta. Right? So this is the theta. The theta is defined as the value that you supply in to the model initially. Right? As I mentioned again, this dependent variable, when you first call the ODINT, the number of theta 0 and theta dot 0 will be passed to theta and theta dot. Right? Then later on, when this result is outputted to the ODE, then the values of theta dot and theta dot will be recycled. Okay, so anyway, we would define the theta to be the first component in the variable, and then this will be a second variable. Okay, so this is how we would do the assignment of the theta and theta dot. So this is just the beginning. We have not really defined our theta dot yet. So we have just defined the values of theta and theta dot. It is assigned a number which is 0, which is 5 degrees, and 0 in the beginning. Then we have to define what is theta dot dot because we want to solve this theta. So theta dot dot, according to this equation, is so just like it here. Let me make it smaller a little bit. Okay, so the theta dot dot should be then I can't see it. Okay, it should be theta. Okay, now my theta dot dot. Okay, maybe then I can see. Okay, so theta dot dot is the shorthand that I use to refer to d2 theta, d theta square, and then it should be then equals to minus omega square multiplied with theta. Okay, so these values of theta is just this. Okay, so okay, let me see here. So this is negative omega square theta minus 2 times C minus omega multiplied with theta dot. Okay, so these values of theta dot is taken from this. Okay, so when you follow the logics, okay, the numbers of the initial values for theta and theta dot is first passed into the model. Then the values of theta would be assigned the values, and so is the theta dot be assigned the initial value. So in this model loop, these two numbers has been defined. Then after theta and theta dot has been assigned some value, then theta dot dot will be assigned a value based on this expression. So this expression, theta dot has to have a value, and then omega has to have a value, C has to have a value, theta has to have a value, omega has to have a value, and it all has a value because omega has been defined upstairs, theta is defined here, and then omega and C and also theta dot has also been defined in the line before that. So when it comes to this line, theta dot dot has to have a value. So these values of theta dot dot will be passed out as a return. So is the values of theta dot. So the theta dot that comes in and the theta dot that goes out, you don't need to define what is theta dot. It's just already been defined. So then these two numbers would then be returned to the ODE INT. So what this ODE INT do is that it will integrate the theta dot and theta dot dot, right? So these two numbers, theta dot and theta dot dot, will be processed by ODE INT. So what it do is the ODE INT would convert the theta dot into theta and will convert theta dot dot into theta dot. Right? See, when you integrate a theta dot, you get a theta. When you integrate a theta dot dot, you get an theta dot. Okay, so the solution for these solutions is it will have two components. The first output will be theta dot and second will be theta dot dot. So I press a button and it seems like I don't got any error. So let me print out. Now I got an error. Okay, so sorry, I got an error because there's no argument of t that has been passed in yet. So I have to pass in this theta, which is the TARR. Okay, so I forgot about that. So this TRR would be passed into the model, so that should be an T as well. So this T is an independent variable that should goes in. So this T and this T are the same thing. Okay. So let's try again. I think it should work. So I'm waiting and it doesn't look like there's any error. Okay, so now you see there is an output. So the first column is this, is the values for theta, and this is the theta dot dot. So to extract the first column, remember what we did? You take a transpose of these solutions, then the solution become a matrix with two rows. The first row would be the theta, and then the second row would be the theta dot. So the theta, well, I said the theta solution is then given by this. Then the theta dot solution is the second component. So then we have almost there. Then we print out what? We print out the TARR versus theta solution. What you expect when I press button? I expect that since the C that I set in is very small, very small, I should see a oscillations with a little bit of damping, but not too much, right? This is what I expect. No, I'm not going to print. I want to plot. Okay, so PLT plot. Yes, I see a simulations that is what I expect. Like it is oscillating and it's dying as it is dumping off. And then you can do a better job. Okay, you want to see if this is true. So what you do is you make the damping to be larger by 5 times. Then you expect that when I press a button, I'll see a more serious damping. Okay, so you see a more serious damping, right? So, and then you can also plot the solutions for theta as well. Okay, so before I proceed on, let me do some labeling. Okay, so I'm going to label the graph, label the x-axis, y-axis, and also label the chart. Okay, so let us do like this. Now the way how I do it is a little bit different. Maybe I should improve on my presentation for the graph. So this is the minimum presentations for the graph, where the graph just gives you the form without the label. Okay, so let me label it. How should I label it? So let me label using Matplotlib. So this is a new technique that I learned, and I'm going to share with you how we do it. Okay, let me add. Okay, so now this is the plot I'm going to do. So I'm going to plot this. So in order to plot this, I want to make it more flexible. So I might have, for example, when you plot, you may have to plot, let's say, 5 different graphs. So for example, you can plot this PLT not for theta solve, but theta dot solve. So theta dot solve is the velocity, angular velocity. So you have 2 plots joined together. Now, what happens if you want to separate them into 2, right? So to separate them into 2, if you don't say anything, the plot that you do would be joined together. So to plot them into 2 different graphs, you should prepare 2 axes or 2 frames. So you say I'm going to have axis 1, axis 2. Axis 1 is a frame where you want to plot the theta. Then axis 2 is a frame which is different from the axis 1 frame. Then you print out the axis 1 and then you print out axis 2 independently. So that is how you can sort of like customize your plot. So what I do is that we're going to do this. So I'm going to call figure. So this is a new techniques, okay, which is a techniques I just learned throughout during the last week. So you said figure and then you labeled your frame. Say there's a first frame called AX1. So usually you use AX to stand for AXE, axis. So you said I'm going to do figure, and this figure has a label AX1. And what is this? This is like this. So this is a standard syntax. I think it's called figure AXE is I think PLT. So what do you want to do? Subplots. I think this is what you do. So what you do here is that you declare that you're going to plot a graph into a figure, and the plot, there's a frame that you prepare, has a reference name called AX1. Then this AX1 is going to be used later part. So you also then prepare another axis, which is another frame. So we're going to plot theta in AX1, plot theta dot in AX2. So then what you do is that you said here I'm going to type AX1, then you're going to type AX2. I think this is how you do it. If I'm not mistaken, this will plot one plot, and that will also plot another plots into 2 axes. Do I get? Yeah? Yes, I get 2 different plots. One is for this one is for the first one is for theta, and this is for theta. So, but you sometimes you get confused because you do not know which one is which. So what you do is that you do a label. Okay, so you want to say label your figure 1. So in order to label your figure 1, which is the AX1, then you just label it lah. Okay, so maybe we just separate the AX1 and AX2 independently and do it one by one. So this is figure 1. And then you plot it. Now, once I plot it, then you can do something. You said, okay, they say AX1. I want to set. I think it's called set, if I'm not mistaken. So you can set many things in the access one. For example, just try it out. Okay, say in the set title. Okay, say title. In this, I think title is say theta versus t. Now, I'm not sure whether this works. I tend to forget things. So if this works, then you will see that there will be a title appearing in the first one, and then the second one would not have any title. Okay, so yes, you see theta versus t. So then that means that this is how you can label the theta in the axis 1. If you want to label the axis 2, which is the second frame, then you just say this is theta dot versus t. So this is theta dot versus t, theta versus t. Then you can continue to label. I think called label. I think label x label. I think called x label. X label is say x. Not sure whether this works. Maybe I've forgotten. Okay, so this doesn't work. Label, sorry, x label. Okay, x label. It works. Yes, it works. Yes. So you see the x here, So you can then label y label, then you said y is theta, right? Theta. So you can copy and paste here, and then you can repeat the labeling for the second axis. This is theta dot. So you see theta versus t, theta, and then this is x, and then theta dot theta. So x. So this is should be theta dot, right? So the label for the y label should be theta dot. So this is how you do it. You can make a better job by saying plotting the horizontal line at x0. So what you do is, I think you can say better. I think here plot, I think you can say here ax1. No? Yes? No? Not sure. So let me plot a ax vertical line. I think called ax vertical line, v line at 0. Last time we have done this before. So this is to plot a vertical line along the, no, I should say the horizontal line. So what I want is I want to plot a horizontal line of the x-axis at y equals to 0. So this is the command that I think it may or may not work. So this is to say, okay, plot me a horizontal line where the horizontal line is defined at y equals to 0. Do I get anything? I got an error? You know, I don't get an error. So I got a vertical line. So that is nice. The problem is that I cannot change the color. So you may find out how to change the color. I do not know how to. Okay, so then you say, okay, for axis number 2, change this. Do I get a line? Yeah, I get a line. So to make sure that things is working well, I wash away all my kernel and begin again, run. So I should have no problem. I should have no error. So the kernel is restarting and it's ready. So they run it. So you have to run it again in order to get the graph to be shown. So this is theta and theta dot. You see that this is like this and this is like this. So you get two plots. If you want to have the plots on to display side by side, I think it is possible. You can do a subplot. I think maybe that is not necessary at this point. Okay, so but you can try to make these two to be arranged on the same row instead of on the same column. Okay, so now there's one more thing I want to sometime to show you, but maybe this is a bit difficult for you because you have no experience in LaTeX. For example, you want to see this is not theta, but theta, but you want to plot this as the forms of theta that you see here. So this theta can be printed on the table on the axis. So let me show you how you do it. So let me change this theta that you see here to be the symbol of the Greek theta. So this is how I do it. So the title, instead of I say theta versus x, now this is what I do. So I say with an R. Then inside here, I will change it into a LaTeX. LaTeX means it's like this, slash theta. That will give you a Greek theta function, a Greek theta word. Then this is VS. Then you print another LaTeX, which is T. Okay. So when you do that, you see theta versus T. Okay. So how about this one, theta dot versus T? So you can do the same thing. So I change the title by saying an R here. Then inside this one, I'll change this into an LaTeX form. LaTeX is LaTeX. So it should be theta, should be dot in a curly bracket, theta. So this command, slash dots in a curly bracket, and in the curly bracket you have a slash theta, would produce a theta dot symbol. Then versus another variable symbol in LaTeX. So the variables or the character that is enclosed within a two money sign will appear as an italic. Is a mathematical mode. So this one is outside the double money sign. So this will appear as just normal text. Okay. So I got some problem here. Theta dot versus. Okay, maybe this is not working. Dot theta. So there is an invalid syntax. So I have to check a little bit. Maybe let me change this like this. I think this one should work. This should be theta dot r theta dot. Okay, so I'm in trouble. So maybe I throw away this r. Let's see what happened. Okay, let me restore the original thing. Theta versus t. So this should be the original one. Okay, this should be working. So I have not changed. So now I'm going to change this theta into a symbol. So this to be changed into a form of string slash theta. Then this is going to be an r outside. Yes, I see a theta, but I'm not going to use a theta. I'm going to use a dot, dot, like this. So that would give me a theta dot versus t. And I want to change this into also a LaTeX form, like this. Okay, then dot, like this. Okay, so I see theta dot versus t. Now this is cosmetic, okay? To change the title into Greek letters, you have to use so-called LaTeX. But if you do not know LaTeX, then just leave it alone, okay? So that is how you can plot these two together into two different graphs. Now let's just do a better job. What happens if we want to plot, say, 2 or 3 different C in the same plot? Right, so so here the C is taken to be just a constant. Right, so I cut out the C and then I put it into here. Okay, like this. So I've not changed anything. When I press the button, the same graph produced, but this graph is producing C equals to 1. Okay, so I want to add in one more thing. I want to add in a label. So here, this I would say label equals to C. The values of C is enclosed in a string, and this is xi. So let's see what happens. When I press the button, I see no C because I have not called the label. Okay, so this is a label that appears in the plot of xy. So when I plot it, I also want to say plot. Well, I said plt legends, legend. Then it will show me the legends. Okay, so I see a legend, but what happened? Module has no legend because of spelling mistake, legend. Okay, so a legend say, okay, this is C equals to 0.5. So let me make some, so the C should be like this. So the C is equals to 0.5. Let me convert the C into the symbol. So in order to convert the C into a symbol, I just convert it and put it into a LaTeX form. This is a LaTeX form. Then with a slash. The slash would convert the, or would generate the symbol for C. So this is a C equals to 0.5. Okay, so what happens if you want to plot another graph where the C is not 0.5 but something else? Okay, so what you do is just that you just put the C into a loop, right? So the C, the initial conditions should be the same, okay? But the solutions depend very much on the C, right? So the C would change. So what I do is that I'm going to put all these things. See, this whole thing would be solved with C equals to 0.5, and then it will be printed out for the graph. So I'm going to put this whole thing and perhaps the this one as well, the theta dot, also into the form of changing values of C. So I'm going to have a 4 C in a range of say 0.01 and 0.05 and then 1.0 and then say 2.0. Okay, so I think this is how you do the C in a loop. Then you have to indent the Python. If you don't indent it, then it would not show. Right? So Python is a bit cumbersome in the sense that this format on the indent has to be taken care of. So when you do that, what happens is that you see 3 different C plotted on the same graph, and then you also would have a C plotted C theta dot as well. So in this case, maybe I should label also the C in the plot of the theta dot. Okay, so plot legends as well for the C dot, for the dot. Okay, so I press the button already. So I see only one graph, two graph, three graph, four graph. Okay, so I see many graphs plotted out. They are not overlapping into each other. Okay, so I don't get them to all merge into the single file. So that is not what I want. But if you do like this, then if you do a plot, then it will all be printed out separately. Now, what happens if you really want to have all the graphs to be printed on the same? Then, in that case, you may not have. Well, maybe you don't use this AX anymore. So I think it's like this. I think plot legend, plot, show plot. Let me try to troubleshoot this. PLT dot show. Okay, let's see what happens if I do like this. And then let me do like this. Do I get all the graphs to be printed out? No, you can't. All the graphs are printed out separately. So I want to print out the graph that all overlap like this. So in that case, now the reason I get this, but here I don't get all the graphs to be printed on the same graph because I am using, I think because of I'm using this one. So I don't use this one, then I may not have this problem. So maybe I would close this, and then I'll close this and close this in order to get all the graphs to be plotted on the same. And maybe I would not want to see the print for the theta dot. Right? So let me show the theta first before I show the theta dot. So by doing that, I'll be able to have the theta dot to be shown. So this is what I'm going to do. So I'm going to plot PLT plot with different C, and then I'm going to say AX, well, PLT dot AX H line at 0, and then there's no more label. Okay, module has no AX line. I think horizontal line, what was that? AXH LINAH line. Okay, so do I get these things printed out? No, it's not printed out. It's separated. So why should it be separated? They should all be shown on the same plot, right? So maybe, okay, I think the reason is because I put the plot PLT here. Okay, so now if you do like this, that means within the same C, you would show the plot for one C. So when C is 0.1, show one plot. C equals to 0.5, you show again. So that explains why you see so many C graph plotted independently. So, but if you were to do this plot outside the loop, right? So what you do is, this plot legend is also outside here. So if you do like this, it makes a difference, okay? So that means it will generate the plots, collected all the plots. Then all the plots will be shown in one shot when it exceeds the loop. So this is to plot the loop, to plot all the graph that is being generated here when you exceed the loop. So I think this will show all the graph in one shot. Yeah, this is how you do it. So now I think I can fix the problem. Let me revert back to the previous example where I used the figure at AX1. So this one, I'm going to close it. I'm going to close it so that I can get the nice plot with axis and with label. And then I'm going to do like this. Okay, I think that should also give me all the plots that will be displayed on the same graph. No, yes, no, no, yes, no. It's just printed out separately. So maybe I should just stop and then restart over again, and then see. Okay, so let me run again. Now I think I should get all the graph to be overlapping. So it's done. No, it's not overlapping. It's all separated. Right. So it looks like I cannot make all these graphs to overlap on the same graph if I use this method to show the graph. Maybe you should be able to solve this for yourself, but at the moment here I can't. Okay, the AX1 are all shown separately, so even though I just print out this one outside, okay, so it doesn't work in that way. But so in order to do that, then I have to revert to the previous example. So I cannot use this method to plot. I cannot use this figure to plot. I just plot it like this. Okay. Then without this AX1 thing, then all graph will be plotted. So you have different C and then plot legend. Here the legend is here. This is the label. PLT, but why is that there's no label shown? Okay, run. Where am I? Okay, so that's the AX1. I think the error here, this one is not. So this is just no vertical line. So that is what I get. But the problem is, I think I do not know what you have found a legend. So there should be a legend. So the legend should be here. But for some reasons, I cannot show the legends for some reason. Okay, so sometimes it doesn't work. But I think it should be okay. Okay, so I think you have, for this case, I just have to put the legend in front of the show. Okay, so that's how you can compare the solutions at different C, right? So for C, which is very small, you see an oscillations, but you see that the oscillation is also damping because the effect is very small. When the C is getting close to 0.5, see when it's 1, then you got this green color thing, which is a critically damped. Then this is an, well, under damped. You can still see some oscillations, but it's not very clear. Okay, so you can make C to be smaller, say not 0.5, say 0.25. You can always keep on changing this to see how it looks like. So if you make the C to be 0.25, that means the damping is not so serious. Then you can still see more clearly the oscillation, at least within 1. But theoretically, when C is less than 1, you should have at least 1 oscillation. So that's how you solve the second order differential equation with this damped pendulum. So this is basically the code that's given to you. Okay, so this is how you show it. Okay. So the last thing I want to show you is this, the free fall gravity. So the free fall gravity is given by this formula. Okay, so now this is slightly different. But not so much different from what we have seen early on. So you imagine you have an object which is dropping, not dropping, free fall dropping. Free fall, yeah, I think this is a dropping of a one-dimensional free fall, which is a function of y. So you can program this quite easily. So this, maybe I should program it for you, or maybe I should just leave it alone. So this is the formula. Well, this is an example of how you do the programming to solve this second order differential equation. Now, to solve the second order differentiation mathematically, you don't need to know the physics. But if you know the physics behind it, it will help you a lot to check the correctness of your answer. So if you know that this is describing a free fall, then you expect the solution of y would goes into an plateau when t become large, and the plateau will be affected when you change the k, right? So damping term, if it's large, that not damping, this is the drag force term. If the drag force term k is large, then you expect that the terminal velocity would arrive earlier, and then and if you switch this k to be smaller, then y would be like a free fall without any drag force. And I think we have talked about this as well last week. So in this case, you want to monitor the solution of y as a function of t, and also monitor the solution of dv dt, right? So where dv dt, sorry, not dv dt, where you also have dy dt. Okay, so you want to solve y as a function of t, and then you also want to solve dy dt as a function of t, where dy dt means the velocity. Okay, so y as a function of time would change like this, and then this is how the velocity change with time. And you see very clearly that indeed when k, which is drag force, become larger, it arrived at the terminal velocity earlier. But if the drag force is smaller, then it would become a straight line. Now this is what you expect from what you learn in Form 5. When there's no drag force, then there will be no terminal velocity, and v will change linearly as time. V equals to u plus at. So the blue color line refers to the case where v is almost equals to u plus at, but it's not exactly at because the drag force is not exactly 0, but it's very close to a straight line. Once the drag force is larger, then you start to see the behavior of terminal velocity. If you make this t to be larger, then you will finally find that this green colored line corresponds to the drag force, which is very relatively minor, 0.01, will also somehow will arrive and then become flattened when t becomes large. And then the y behavior will goes into this limit. When y, when the terminal velocity, when the k is very small, v would varies according as a parabolic, like y equals to ut plus half at squared. So the y would evolve as a function of t squared. So this is the graph, which is y evolving as t squared. So these are all the details which I'm not going to go into. Last week we mentioned about this. So basically, just like the same thing, you define your y, and then you define your y dot, then you define your y dot dot, then you return the y dot and y dot dot in the model. Then you call the solutions, ODE, you put in the model the initial conditions. So the initial condition for the y naught, which is 0, initially is dropped from 0. Then you put in the loop, then you solve it, and you print it out like this. Okay, so this is kind of straightforward. Now, I'm going to show you another thing, that is to solve a two-dimensional projectile motion under gravity. So this is what we're going to see here. Now, basically, everything are almost the same, except that here we are trying to solve two differential equations at one time. Two second-order differential equations at one time. But this is going to be a little bit I need some explanations, okay? So basically we're going to solve this later and to show that the solution for this can be achieved, and then what you want is to see how the y change with t, x change with t, and then when you combine x and y together, eliminating the t, then you should see a parabola representing the projectile motion of 2D, okay? So we take a break for the moment. I'll give you a chance to sign your attendance. I think it's here. So we come back at say 4:10 after 6 minutes later. Any questions you can ask me. We should be able to finish this today later on, at least chapter 9, section 9. Okay. Okay. So we'll take a break now. See you at 4:10. Okay. So I'll switch on my recording on the screen. So let's see this one. Okay, so we are going to talk about solving a simultaneous equations. Now, well, not really a simultaneous equations, but these equations. So let me see my versions. Okay, so my version is slightly different than yours. Okay, doesn't matter. Okay, so let us look at the solution we want to solve. We have two differential. In this case, we have a projectile motion, 2D projectile motion. So you launch a projectile motions with some initial velocity, and v naught cos theta and v naught sin theta. Then initially is located at x is 0, y is 0. So when you launch this projectile motion, Newton's law gives you an equations that governs how the x and y coordinate should change with time under the gravity. The y components of the projectile would be under the influence of gravity. So when you write down Newton's law, Fg equals to what? F equals to G. So the force that acts on the object vertically is mg, right? Then so vertically the formula for the acceleration is m times the acceleration along the y direction. So this is may on the left hand side. So may refers to the accelerations, and the acceleration is given by the force that acts on it vertically, which is the gravitational force pointing downwards. So this is F equals to ma for the vertical motion, where this is a force going down, and d2y dt squared is the acceleration along the directions of motion y. And along the x directions, there's no force. So the formula describing the x coordinate is d2x dy dt squared. So when you solve this d2x dt squared equals to 0, then you will have a solution for y and also solution for x. So we are going to solve two equations at once, and you should see the solution for y would be a pendulum. It would be an object which is dropping under free fall, and then the x component is a movement along the constant velocity along the x directions. And the solutions analytically would be this. This is y equals to ut plus half at squared. That's the formula that you memorize for free fall. And then for v, dv dt, well, vx, which is dx dt, is 0, right? Because because there's no force along the x horizontal direction. So when you integrate this for the x component, then the velocity along the x component, I think this one, vx would then equals to be a constant. This is equals to the constant you begin with. Vx naught is a constant initially, which is equals to this number, v naught cos theta. So we assign initial speed to the projectile motion, v naught. Then the initial conditions for the v along the x direction will be v naught cos theta, and then the initial velocity along the y directions for the projectile will be v naught sin theta. So this is a v naught sin theta, not v naught. So there's a slight, yeah, this should be a v naught. Okay, so I just corrected the symbol. Okay, so this should be v naught sin theta. Okay, so the solution is well understood, right? So you learned this when you was in Form 6, right, or in the matriculations. So the solutions would form a projectile motion. So when you solve it, this is what you will see, right? So we are going to solve these equations and then see how it looks like. So I'm going to plot this. I'm going to do all this number. Now, before we begin on, you have to know how long you want to simulate. So you want to simulate it like it's a pendulum, it's a projectile motion that starts off from some initial values, then it flies through a parabola. Wait, you have a parabola like this, right? So it runs from here and then up to the maximum, and then it will fall down again and then go through this and go down. So the time scale you want to solve for should be expressed as in terms of the time taken for the parabola to reach to the half of the maximum. This time of the half maximum is 2 times for the parabola to reach from this point to this point. So the time scale can be taken to be the t half, which is the time taken from here to the maximum point, or could be taken as 2 times from here to the same height, right? So this is defined as t half. So I define the t half to be the time to reach the maximum, and you can calculate very easily when you reach the maximum using this very simple formula, v equals to u plus at. But at the height, the velocity along the y component is 0. So v equals to u plus at, and you set v equals to 0, then the time to arrive at the maximum is just the velocity v naught initially divided by g, right? So this is the time taken for the projectile to reach its maximum. So you should simulate it for the time from 0 to say 1, 2, 3, half. Right, so I'm going to simulate it for this amount of time. So I'm going to cut and paste this one, and then let me see. I can, if it is possible, I would like to reproduce this result. on these screens. Okay, so this is the initial condition that I need to. So initial condition is that x naught y naught is 0, and then this is a constant. I set the initial speed to be 1, and then theta is a launching angle, 45 degree. You can make this 45, you make it 30, whatever. Then this is the time scale. And then I want to simulate it for 2-point time scale. Right? 2 half means that the time is going from here to here is time half. So if you go from here to here, it's 2 time half. Then going to here again will be 3 times time the t half. But it doesn't really matter. But at least it has to be like more than 1. So I'm going to say this to be 2.5. 1.5 is also enough, but 2.5 is just a sim. So I'm going to simulate this, and then I'm going to generate 50 data points between t0 and the last time I'm going to simulate. Right? So the parameter t is an independent parameter. So let's see what we're going to do next. So you have to define your model. So you can have this. Like here you said my model. Okay, so this is say you define your model to be, so the model would be an independent dependent variable, and then this is your input. Okay, so you have a dependent variable. Now let's say I just want to solve for the y, right? So y and y dot. So let me solve only the y component first. So let me put these equations, just this equation into my equations, and then I'll solve it and plot out the solution for y. So I'll call my y to be the 0th component, and then I'm going to call my dy dt to be the 2nd component. Then I'm going to define my y dot to be minus g. Right? Y dot minus g is just to generate the expression for this. Okay, and then I have to provide the initial condition of y naught and then b y naught. So let me define my initial conditions. So initial condition would be a number for y at 0 and then dy dt at 0. Okay, so where is my dy dt? Now dy dt dot is the velocity, right? So dy dt dot is the initial value of the velocity. So what is the velocity? It should be v naught. V naught is the magnitude of the for the speed initially. The y component of it would then be sine theta. Right? So sine theta is 45 degrees. So the initial speed for y, I call dy dt, will be this, and then the y naught is the initial number which is being launched. So it being launched from the coordinate of 0, 0. So that is how I put in my initial condition. Then I'll call my solution equals to ODE int. The initial condition would be model, and then my initial condition, and then the TARR. So maybe is that done? I'm sure. Let me press the button, and then it has many error because of the size return, blah blah blah. So what's the problem? Y naught is 0. dy dt sine theta, I do not know what's the problem. Anyone can tell me where is the problem? dy dt naught model. So there are two conditions. Solution init condition. Initial conditions. Let me see. Init conditions looks like it's correct. TARR is also looks like it's correct. So maybe my TARR is not right. No, it's right. Y naught equals to 0. Dy dt naught. Okay, let me check again. Output. The size of the array is not matched with the size of y0. So y0 is not. So that should be, okay, maybe this is y0. Y0 is already been defined to be 0. Okay, so maybe I should not define the y0 here. But still I have problem. dy dt, maybe there's no return in the model. Yes, maybe it's not, maybe it's definitely true. There's no definite return. Okay, thank you very much for reminding me that. So return two output. The first output is y dot dot is the second one I want, right? So not y dot. Well, this y dot is just this dy dt. Okay, maybe I just call it y dot. Okay, so I have y dot and y dot dot. Let me press the button. It looks like there's no solution, no error. So let me so the y solutions would then be the solution transpose number 0. Then the y dot solution, which is the velocity along the y directions, would then be 1. So I want to plot then plot TARR. So I want to plot y solution. So what I expect is that I'll see y equals to a solution that looks like this. So this is what I expect to be a parabola as a function of time. And then the velocity v should be a straight line, right? So dv dt, sorry, not dv dt, v, which is the slope of dy dt. Okay, this is, sorry, y dot dot should be just a constant, right? Y not, vy is the solutions. So v is a, sorry, v would be dy dt. Dy dt would be then, yeah, I think this is the solution. So I expect that the velocity, which is y dot equals to vy, is a increasing with time with a negative slope. So it's a straight line that is in opposite direction. So this is what you have already expected. If you can still remember your Form 6 physics, then this is plot. Then I'll call this. So indeed, yes, this is the parabola of y equals to ut plus half at squared. And then when I plot the y dot solution, that is a straight line. The straight line with negative. Okay, so it looks like it's correct. So I got my v dot and v dot dot nicely. So now let us try to solve the solution for x. Now what you do is that you can define another model. So this is a model for y. You can define a model for x. So but let's just try to not to do that. Now what I'm saying is that you can try to define a model for x. Then you define this to solve your x solutions. This should be then 0. This is 0. Then so x dot is equals to this one. I think this is this y dot is equals to this. Maybe there's something wrong with this. So let me check again. Okay, let me finish this one. X dot and x dot dot. So okay, so let me recycle it, and then this should not have any effects because I do not call it. So I run it. I want to see whether the solution is still intact. OD is not defined. It's not defined because, okay, I forgot to cut and paste the solutions. Okay, just let me cut and paste this size. Control C. Okay, so let me cut and paste this. Okay, so yes, so this is still intact. So if I want to do it, then I have to define a model for x, and then the first component in the model of x, and then the second component of model of x is x dot, and this is the equation. X dot dot is 0, right? So x dot dot is 0. Now I just want to warn you, it may not work in this way for some reason which I don't explain, which I don't understand really. So d2x dx square, d2x dt square is x dot dot. So this is how you do it. So then let us call and plot x instead. So maybe I just don't plot it. I just comment it out so that there's no output from this. Okay, so let me just look at the solution for the y. So I'm going to say that dx dt dot is the initial speed of the x component, and the initial condition would be x0, and dx dt not solution x is a model with initial condition. So this is initial condition for x. So let me label this as x, and this is labeled x so that you don't mix with the solution for the y. I call this x solution. Then x solution is solve x dot t. This is x dot solve x, and then this x dot solve. I think this like that will be fine. So just a change of name. So I'm going to type x solve and then x solve x dot solve. So when I plot, I expect what? I expect the solutions to be given like this. X would be a linear functions which increase linearly with t, and then v, which is dx dt, the vx, which is vx dt, x dot basically will be a constant. I should see a constant, horizontal constant, and x that is increasing with time. But I doubt that I may get the solution. I may get the correct one. I doubt it. Okay, let's see. Press the button. Yeah, I got it. This is the x, which is a constant. It looks like constant. No, it's not like this. So let me clear the memory. Just make sure that what I print out is correct. So this is to be printed out. PLT. Okay. So just run and see what I get. Nothing. Okay, let me print out again. Run. Yeah, it looks like it's a constant. It's a constant. It should be a constant. So I'm not sure. I want to see whether the vx x dot is it a constant. X dot solution x dot. So let me print out this one. I just want to check that this x dot solve, it should be a 0. It should be a constant. X dot solve. This should be an array which is a constant. So it's not really a constant. It's changing with time. So it's so weird because the x dot solve should be x. Sorry, no, I think it's quite true. No, this is the x solution which is changing with time. I'm looking for x dot solve. Yeah, it doesn't look like it. X solve is increasing with negative. So no, I'm not sure which one is which. Maybe I should just print out this one. So I'm going to print out this as a red color dot, and then I'm going to print out this as a dot, black color O. Okay, so R dot is this. So this is the X, and this is the Vx. So this is not correct, isn't it? Because this one, according to this dot, is a solution for X dot. X dot solve is decreasing with time, and it starts from minus something, it goes to this. But do you expect that to happen? No, because expect that Vx, the Vx should be a constant. Okay, so you expect it to be a constant, but it doesn't show me a constant. It shows me something which is different. I think, therefore, I suspect that you got an answer, but the answer is not correct. So let me check again if there's any problem. So x is the first variable, x dot is this. The initial condition is that x naught initially is a constant, which is 0 initially. So x naught initially is 0. And then x dot dot is the output, which is 0. X dot dot is 0. So you integrate x dot dot, you get xt. So let me check again. X solution seems to be correct. X dot solution to be correct. So when I plot it, yeah, it's same thing. So the x solution begin with 0, and then it is getting larger and larger and larger, and then somehow it arrives at negative. So you start at V0 and point something, it becomes larger. So it's not really going in a X dot red color. Yeah, so this is what it says. The X is not increasing. Maybe I have done some, it looks like the V and X are oppositely defined. Let me see. The solutions, initial condition, yeah, it's X naught, X T naught. X is this, X T naught is this. Dependent variable looks like it. X solution, X dot solution, X dot solution. Yeah, model X in, yeah. So this should be model X. Thanks very much for reminding. So this should be model X, not X. Okay, so this should be model X. So you should call the solution should be model X. Yeah, that is what I expect. Thank you very much. See, this is always can be confusing if you're not very careful. So I have changed the model X. Then I got this. This looks much better. So the red color dot is an X solution. So yes, the X is increasing with time. And then this is constant, right? So the X is plotted constant. And then, no, maybe I should just say figure PLT dot PLT dot figure 1, and then I say this is figure 2, then it may be plotted in two separate figures. Okay, so this is T, X changes to T, and then this is velocity, Vx, right? The Vx is a constant. So it looks like we have very nice results that looks almost the same. Now, if you look at the code that you have in this example that I give you, now I code it slightly different, okay? So this is, let me see. Okay, here. So the way how I code it is slightly different. What I do here is that I put the X and Y into a single model instead of separating into model X and model. Okay, so let us try to do this, okay? But I think there might be some possibility that I might get it wrong. So now let me try to do it again. I'm going to merge the two models together, okay? So I'm going to call X dot, Y dot in my dependent variable. So I'm going to do a new thing. So now I am going to merge these two together. So how do I merge them? So there'll be only one model instead of two. So in this case, the dependent variable would be 4 input. The first one in the dependent variable will be X. Second one will be X dot. And Y dot. Okay, so that is what I plan to do. Okay, so I'm going to change my Y and Y dot to be slightly different. So I'm going to call this X1 to be the first component variable, X dot to be the second one, and then Y would be the third one, and Y dot would be the fourth one. Then I have Y dot dot, and I also have X dot dot. X dot dot would be 0. So this is my definition for my Y dot and then X dot. Okay, so maybe I should just rearrange so that I do X first, then I do Y, so that it doesn't mix. X dot, okay, like this. So by doing this, when the loop is entered, it first assign X and X dot, then it assign X dot dot, then only assign Y and Y dot. So the output will be 4. There will be 4 output. The first 2 would refer for the X component, and the next 2 is the Y dot dot. So in that case, we will not have any X model. Then there will be 2 initial conditions, dx and dy. So I'm going to just throw this away first. So there will be X solution. There will be solution. Okay, let us do it one by one. Okay, maybe I should. Okay, so this is the initial conditions, dx naught, dy naught. Okay, so in our case, we have 2 initial conditions, but 4, 2 for X and 2 for Y. So this is initial condition that we're going to put in for x. Then we're going to put in the initial condition for y. And then this will be dy dx. So I make sure that the dy dt naught is defined and dx dt naught is defined in the initial condition. And then there's only one solution. Then the solution would be calling in this one. And then, yeah, I think that is more or less the same. Okay, so that would be using 4 initial conditions so that we can solve x and y at one shot. Then after this line, the solution should have been obtained. Then we extract the x solution as the solution from the first component. Then the x dot solution would be the solution for the second component. Then you expect the solution for y would be the D2, and then this would be D3. So this would be y solution. So then I'm going to throw this away, and then I'm going to plot the graph. So not sure whether this will work, but anyway, let's try. So what we do is that we have to figure, well, let me say PLT dot figure 1. I'm going to plot PLT. I'm going to plot what? Plot TARR for x solution. So that is what I'm going to do first. Then I'm going to plot the other 3 more solutions. So I got error as usual. Matplotlib has no figure because of PLT FIGUR. Yeah. So that is my solution. So this is a solution for T. So I'm going to say this is the label. Label equals to x versus t. Right? So this is x versus t. Maybe I just call this plot legend. Plot PLT legend. Legends. Okay, so I have 1 functions obtained. Now how about the solutions for x dot? Okay, so I'm going to plot the solution for x dot in figure 2. So this is x dot solution. This is called x dot solutions. So I get anything? Yeah, this is x dot solution, which is constant. This is what I expected. Right? Then I have another x, y, and y dot. Right? So we are going to reproduce in the figure 3 and figure 4 for y solution, label for y, and then y dot solution. So y dot should be a parabola. Right, so I expect that in figure 3 and 4, I should see a parabola like this. No, this is not parabola, y dot. So something is wrong. Dot solution, figure 3, TRR, y solve, y dot solve, y dot solve, solve 1, 2, 3, 4. So there is a little bit of problem I'm facing. I do not get the correct answer as I expect. Okay, let me clear all the memory away. So this is the solutions. X solve, x dot solve, y solve, y dot solve, and then the first 2 figures seems to be correct. Then this one and this one should be correct. So let's run again. Not get anything. X versus t looks like x dot versus t looks right. Y versus t is all 0, so I'm in trouble. This is not what I expect. Y dot should not be like that. So I think there might be some problem because of the way how I assign x and t independently. So x dot like that. So this should be v0, v1. Okay, this is the solution. Okay, I think I make a mistake. So this should be 3. Okay, so that is a mistake that I made. Okay, let's press the button again. Y, yeah, this is a y with a parabola, and then the velocity of y is increasing linearly. So we have now solved the 2-dimensional problem, x as a function of t, y as a function of t, and then blah blah blah. So now let's just combine and plot y versus x. Right? So you can easily plot another figure 5. We are not going to plot TR. We're going to plot x solution. and then y solution, right? But now x and y solutions is what? X and y solution. Let's see what is x and y solution. X of, yeah, it looks like this. Y should be similar. So I think I should be able to plot x and y at the same time. And then I got x versus y. X, y versus x as my graph. Okay, so this is the fourth one, which is this one. Right, y versus, so what is this? This is the parametric y equals to x squared. Right, this is what you expect when you combine y and x together. Now this graph is y versus x. You should not confuse this with this graph. This is y versus t, right? So the x-axis is time, so it's 0.175. But for this one, this is the maximum distance travels by the pendulum along the x directions within the period of simulation. So this is the trajectory of the parabola, right? So if you want to make these things look slightly better, then just plot, just say plot ax vertical horizontal line at the point 0. Then you got this very nice. Sorry. I'm sorry. There's something on. Okay, sorry. So this is the parabola that is well known to you. So we have shown that yes, you can solve two simultaneous differential equations of d2x dt square and dx d2 square dt square in one shot. Okay, so that is the solution. Now the solution I have here is slightly different. Okay, slightly different than the one that is given to you. Right. So this one that is given to you slightly different, where I solve x in a different way than this one. Okay, so the graph that I have here is slightly different. So what I do is that maybe I just add in one more thing here. Then I just paste on here as the solutions that I just shown on the graph in my own version. Okay, so this is the one that I just done. So this is a solutions where you solve x dot and y dot, x dot and y dot in the same graph. Okay, so let me save it. So if you access the same file again from Moodle, you get my code that I just prepared. But at the same time also, the code that is being shown to you here is to show you three different trajectory shot at different angle. Okay, so you have here a different angle, which I can do it here as well if I want to. So maybe I just so this is the solutions for one angle only. If you want to have a few more angle, it is possible. You just have to do this. Just put all of this into a single figure. Then you will be able to know. Okay, maybe I just do it. Okay, so for theta in say 45 degree, and p dot pi over 4 is 45 degree, right? So it's 45 degree, and then you can make it to be less than 45 degree, maybe half of 45 degree. Yes, wait, I got, any one of you are talking to me, or this is someone else? 0.5. So this is half of 45 degree, and this is 45 degree. So if I want to have another one, where am I? Okay, so here. So I can have this to be 0.75. So I have three different angles by putting into a for loop, then I'll be able to print the figure. So maybe just throw away all this stuff. Just plot figure 5 would do. Okay, so in this figure 5, I just plot dot legend, and then I just, okay, wait. Then maybe I should cut off this okay, fine, so that it don't confuse me here. Okay, let me come back to my code. Okay, so this is where I start with. So I'm going to say BLT show. Okay, so that is how I do it, right? So I have 3 different angles, 45 degree, 7.5. Okay, 7.5. So this is 45 degree in the middle. Then this is half of 45 degree, which is like 22.2. This is, I think, like 75 point something. So so I have 3 different angles shown, 3 different trajectory. So this is very similar to the one I given here. It's just that I plot using this dot. Okay. So after this, you should be able to show how this second order differential equation is solved. So if you can already solve this, then you should be able to solve your next tutorial. So your next tutorial is this, right? So next tutorial is assignment 9. I think this should be a little bit complicated. So let me switch on the tutorial 9. I think the tutorial 9 is slightly more complicated. So the tutorial 9, I'm going to switch it on. You can download and see for yourself. So it's going to be for 1 week. So today is 19. So due date would be 7 days after 19. 19, so it should be what time? So 7 days later, 19. Next week will be 26. So I'm going to set this to 26 as your assignment. 26. Then this is 26. 26. Okay, looks okay. So save. Now your assignment number, assignment 9 would be to ask you to solve the differential equation for the damped pendulum for different cases. So just repeat what I have given you. It should be quite straightforward. So you just key in and then solve it and plot the graph. Now this is more challenging, right? So this is a planetary motion. So it's a second order differential equation in R dot, right? So you're supposed to solve the second order differential equation R dot dot. So R dot dot here means that dr, d2r, dt squared. And then you have a single variable of R change with time. Then GMM and L are just constant. Then at the same time, you also have theta dot. The theta dot is the angle that change with time as well. So there are actually 2 variables in this case. You have R, which is this one. So this R is this. It's not labeled, but this is R between the Sun and Earth. And then you also have an angle. So this is the what they call celestial mechanics. Celestial mechanics means equations, mechanical law that governs how celestial objects move around the planets, move around the sun in the sky. Okay, so the equation that governs this is the Kepler's law. The Kepler's law derived from Newton's law. But this is the Newton's law written in polar coordinate form. Right? So if you write down or memorize a formula for object of sun, Earth moving around the sun, you have mv squared over r equals to gmm over r squared. Right? This is the Newton's law for Earth going around the sun in xy coordinate. But if you write it in polar coordinates, the equation would look like this. So instead of x and y as the coordinate for the Earth, you have r and theta. So this is the coordinates in polar form. So you have, instead of x dot dot, y dot dot to describe the change of the coordinate as a function of time, you have r dot dot and theta dot dot, right? But in this example, you don't have to deal with theta dot dot, but you just have to deal with theta dot. Theta dot dot and r dot dot, well, to be more specific, theta dot and r, they are related by the conservation of angular momentum. But the physics is, you can do the solution without knowing the physics. You just have to solve the second order differential equation in terms of r dot dot. Right. Then you are given the fact that the r squared times theta dot is a constant. So this corresponds to the conservation of angular momentum for a planet going around the sun, and this L is a constant, right? Then you are given this parameter, the Earth-Sun distance, semi-major, semi-minor distance, and the gravitational constants, and the period of Earth moving around the Sun, right? So A is defined as the semi-major. So the Sun is located at the focal point of a, this is an ellipse, okay? It's an ellipse. So it's not a circle, but it's a general case of a circle, which is an ellipse, where the x axis and the y axis for the orbits are slightly different, right? So the x axis is longer than this y axis is smaller. You call it semi-major and semi-minor. So your job is to write in Python code to solve the second order differential equation for the y. For the r, which is the radius of the sun from the Earth from the sun, right? So r is the distance between the Earth and the sun. So the r would change, right? So if the Earth is here, the r is smallest. It's called perihelion. And when the Earth is located here, then it's furthest away from the sun is called epiheron or whatever. So r changes with time. So it's an angle, right? So when theta is 0, when t is 0, theta is 0. After half a year later, the theta becomes 180 degrees. After 1 year later, then the theta will become 0. So the theta is sort of like going in a sinusoidal function. So your job is to solve the differential equation for r, for theta. Right? So you're going to solve r dot and r as a function of time. Then you have to solve theta dot and theta as a function of time. But you don't need to solve the theta. But you just have to see how we do it, because the theta dot is given in terms of this constant. Once you know what is r squared, then you should be able to obtain the theta dot. Then you integrate the theta dot, you'll be able to get the theta. So your job in this case is generate this graph. Okay, generate the orbits of a sun moving around, the Earth moving around the sun. So finally, this is what you get, right? So when you finish it, then you should be able to generate the plot. So you do it one by one. First of all, you calculate r as a function of time, and then you calculate r dot as a function of time. Then from there, you calculate the theta dot as a function of time. Then you calculate theta as a function of time. Then you combine the r and theta and show it into this form. But this is a tricky question, because all the solution you are asked for to show has to be in a reduced coordinate. That is, you don't solve for y and x, but you solve y over a and then x over a, where a is a constant, the semi-major. And the theta has to be expressed in terms of the unit of the period, right, which is 1 year. So you go and read this and then try to understand this, and then follow the solution, follow the instruction and plot all this graph. It should be quite straightforward, but you have to use your brain a little bit. So this is a challenging question, right? So if you can solve this, then I'll be very, very happy, provided that you solve it for yourself, but not copying from elsewhere. Okay, so this is your assignment. It would occupy you for quite some time, but idea is the same, right? So you solve this, then from there you obtain r and r dot. Then from there you have to calculate r theta dot, and then the trick is that to obtain theta, you have to obtain the theta, well, from some tricks. You have to figure out how. I think the difficult part is to obtain this function, theta as a function of time. Now once you know how theta changes with time, and you know how the r change with time, then you can combine r and theta into X and Y and plot this graph. So there's a lot of changing of coordinates. So, but it's a good test for how good you understand the application of physics. You learn a lot of physics, you learn a lot of mathematics, you learn a lot of programming technique. Now is a time to show to the whole world how you can apply your knowledge, right? Okay. So that is your assignment. Now you can always ask me any questions. If you have any problem, send me emails or send me an WhatsApp, then I'll try to help you on that. So the next bit we want to do is a more interesting part, which is on the simulation, right? So the next thing will be more interesting. So when you look at the simulation part, it's like this. I think let me show me my simulation. The simulation. Where is it? So I'm talking about the part 10, right? The part 10 would be to show the simulation. For example, in your assignment here, you generate this one. So can you show how the dot changes as a function of time? You know how the pendulum change with time. Can you simulate the pendulum? So I think this is what we are going to have. So if you have a pendulum, you know how the pendulum change with time. You can show it. Then all you have, okay, so this is just to run and show, just to impress you, okay? Do I get anything out? No, I don't. Okay, so not this one, maybe this one. Okay, so we're going to show you how to do this simulation. So you know how this pendulum changes with time. Then you can display it on your Jupyter notebook. And then also this is a very simple example of a 1D wave, right? So you have learned in your 103 how wave would change with time, right? So a wave is described by these equations. So you know that when time changes, then the wave will just like sort of like moving towards or moving backwards. And one sinusoidal wave is given by this formula. So x is the position, t is the time that keep on changing. So if you evolve the time from 0 to 0.1, 0.2, 0.3, then the whole profile of the wave will change with time, right? So you see all this in your 103. So let's see how you do it in this case. So you can actually plot and show this. And I show this one is not showing. For some reason it's not showing. Let me change it again. I think the simulation function in Python is not as friendly as Mathematica. Mathematica gives you a much better way to do a simulation. Python is not good at simulation. It's not as convenient. Okay, maybe here. Not this one. Okay, maybe, yeah, maybe this one. Yeah, maybe this one. Okay, so you can see that wave actually simulates and is moving, right? So it's moving to the right hand side, moving to the left hand side. So this is what we are going to do. Now, once we have finished this one, then you'll be able to say generate a graph like this, right? So basically, if you know how the coordinates of each point changes with time, you can write down the equations of how the x and y change as a function of time, work out the formula, then you have to translate that formula into the graphical form. Then you submit this as an assignment. So I'm going to find out a few more assignments that looks like this, and then you're going to choose one, but not now, maybe next week. Okay, so I just want to warn you, next week on Tuesday, we have a test. So we are running out of time. What kind of test is that? I haven't figured out yet, but just warn you, next week I'll give you a test. I think the test may be 1 hour or maybe 2 hours, depends on how difficult. If it's 1 hour, that means it's relatively easy test. If it's 2 hours, that means it's slightly more difficult test. Okay. So it's 5:01 already. So I thank you for your attendance. So any questions you want to ask me? So just to conclude today, I'm preparing a project list. Once it's finished, I'll display it, and then you have to find out one partner. Both of you would be combining effort remotely, then do a project, submit the code as well as a PowerPoint report. You have to submit a report, mostly in the form of a PowerPoint. And then next week, we are going to have a test on Tuesday, same time, 3 to 5 o'clock. Next week is sem break. Sem break, that means there's no more break, isn't it? There's no more time. So next week is sem break. Sem break means what? You finish already your class. That means you don't have to attend anymore. Your class, all the other lectures has finished already, is it? But we have to have Hari Raya break. Okay, so Hari Raya break, not sem break. So Hari Raya break, fine. So if Hari Raya break, that allows you to break. So when you come back from your Raya break, we will continue the test. So maybe I'll let the test to happen the week after you come back from Raya. Would that be okay? Okay, so if there's no response, then assume that you will come back after your Raya, then we will have a test after that. Okay, fine. So that's all for today. When there's any update, I'll let you know. I'll send a bulk message to the WhatsApp. Okay, that's all for today. Thank you very much for your patience. Okay, bye.